If you explored the materials on high-performance HMI principles, I'll link below chapter 4, which I really hope you did. You probably noticed that the focus isn't on displaying raw data, but rather on presenting information that's actually relevant to the operator's task. For example, if I tell you that the current supply water temperature is 65 degrees Celsius, what does it really tell you? It's not nothing, but without context, it's hard to say whether the system operating correctly. Now compare that to showing how the value is changing over time, whether it's rising or falling, how fast it's moving, what the current set point is, and how all of that fits within the normal operating range. That's when you start building real situational awareness for the operator. And that's exactly what we're going to do today, but we'll do it a bit differently than usual. First, I'll show you what I've come up with, and then we'll walk through the creation process step by step. So, ready? Then grab yourself a cup of something and let's get started. We already have the heating subsystem overview screen we've built earlier. On top of that, I've created a dashboard screen. It takes all the analog values we already have, temperatures, pressure, speed, and represent them as bar graphs. The reason for this is simple. The human brain generally understands information faster and often better when it's represented in an analog form. Gauges, bar charts, graphs, and similar visuals. Think back to the Airbus 320 example, or let's use more down-to-the-earth one. Yes, pun intended. Your car's dashboard. Speed, engine RPM, fuel level, all the values you need to read quickly are usually shown in analog form. Let's go from left to right. First, there is a vertical temperature scale from 30 to 80 degrees Celsius, attached to an empty rectangle that acts as a visual anchor. On top of that scale, a blue triangle moves up and down to represent the current supply water temperature. Sometimes it's called a needle. The exact numeric value is shown below the graph. To the left of the needle, there is a small temperature graph showing the last 5 minutes of data. This is often called the spark line, and it lets the operator quickly see how the value changes over time. To the right of the triangle, a blue diamond shows the temperature set point. If you remember the Intro to a CP600 course, this comes from T1 output of the temperature graph. When the triangle and diamond are vertically aligned, the process follows the set point. If the triangle is higher, we have an overshoot, and if it's lower, an undershoot. The light blue vertical band, which extends to the left with dotted lines, marks the normal operating range. And finally, to the right of the temperature scale, there is a valve opening-closing scale. A blue indicator shows the control action, from 0 to -100 for closing, and from 0 to +100 for opening. Supply water temperature, T1, and valve open-close commands are all parts of the same control loop. That's why it makes sense to display them all together. Return temperature bar graph acts exactly the same. The only difference is that set point diamond is linked to T2, and to the right we have pump speed, because return temperature is controlled by accelerating or slowing down the pump. Now let's move to the pressure. And this part works a bit differently. On the left, we have the discharge pressure value along with its trend over time. On the right, there is another needle showing the suction pressure. For pumps, the key parameter is the head, or in simple terms, the pressure difference the pump creates. That difference is visualized by the blue bar in the middle, spanning between the two pressure indicators. If the pump can't generate enough pressure difference, It's a clear signal to the operator that something might be wrong. On the bar graph, pressure difference falling below a certain level is highlighted in red. At the top and bottom of the main bar, there are critical pressure zones that also turn red when either pressure enters them. For example, suction pressure dropping below 2 bars could lead to a dry run condition, while discharge pressure rising above 14 bars might indicate a blocked pipe. The ambient temperature indicator is the simplest one. There are no limits, normal bands, or set points. Just a scale, a needle, and a trend over time. A 30-minute time span makes more sense here, since ambient temperature doesn't change that quickly. It's worth noting that ambient temperature is a rare case of data that provides sufficient context on its own. If I tell you it's minus 10 degrees Celsius outside, you already know it's cold. You don't need additional context to interpret the value. Frankly speaking, we don't even need a bar graph for it. But that's rather a unique case because we are daily exposed to weather information. How often do you think about exact temperature in your water tap? Okay, now is the part for those of you who wants to know how to make it. Let's switch to Panel Builder and develop that dashboard. So yeah, we could have used the vertical gauge widget from the meter folder. It works. For example, if I set the value to say 60, the red needle moves up. You can define the min and max of the scale and tweak a whole bunch of other settings. But personally, I find it a bit fiddly, especially when it comes to resizing. The scale, text, and needle all get stretched or squashed. And then if you want to change the needle, it's technically possible in settings, but almost never looks as you intended. Because of that, and also partly for learning purposes, I'd rather build everything manually myself. Start with the rectangle that will act as the backbone of the whole indicator. Then drag a vertical scale widget from the widget gallery. Set the alignment you need, then define the maximum and minimum values. We don't need alarm ranges here, so set that to 0. Same for minor ticks, set them to 0 as well. Set the number of major ticks to 6, so the scale is easy to read across the full range, and reduce the tick size a bit. Now double-click the widget to get into edit mode. Adjust the text labels to make the scale more compact. Move the numbers closer to the tick marks. Tweak the font size and color, and fine-tune the positioning of the elements. After a bit of cleanup, you should end up with something like this. Now that we have the scale, let's add a needle to show the current temperature value. Insert a triangular shape and move it to the bottom of the scale. That's our minimum temperature position. I'll zoom in a bit so it's easier to see what's going on. At this point, the needle's y-coordinate is 372 when the temperature is 30 degrees, and 123 when the temperature is 80 degrees. Let's write these numbers down. They will be very helpful in the next step. So, how do we get the needle to move when the temperature value changes? The most straightforward approach is to link the y property directly to the supply temperature tag. But the range of values is different and y-coordinate is inversely proportional to temperature value. We can use scaling, I hear you say. That's a solid idea. We can set our input range from 30 to 80 and map the output to the coordinate values we established earlier. This works fine until the temperature moves outside the 30 to 80 window. Needless to say, that's not what we want. The needle has to stay clamped within its limits, even if the process value drifts beyond defined range. What's the solution? Well, we can still use formulas. Even though there isn't a dedicated clamp function, we can build one ourselves by nesting min and max functions. Here's the formula. And here is what the implementation looks like in Panel Builder. That should solve the problem, right? Not exactly. As it turns out, using a formula disables the scaling functionality. The two features simply can't run simultaneously. Where does that leave us? We can actually build our own scaling function directly within the formula editor. Ultimately, scaling is just a combination of basic arithmetic operations. We've done it already in PLC. Here's a quick refresher on the math behind scaling a raw input across specific output ranges. First, let's make things a little bit easier by using internal tags. Now, is there anything wrong with the existing controller tags? Not at all. Ultimately, we'll still be using them. The issue is that when you're composing a formula using a PLC tag, you have to use the full path. When you start adding 2 or 3 tags in a single expression, it gets messy, since we only have one line of space for everything. Therefore, I'll go to the Protocols section, add a new protocol, and select variables from the drop-down list. Then, in the Tags section, find the Variables item and create a new tag, for instance, a floating point input variable. This tag resides strictly within Panel's memory. It's not linked to anything and you can change its value. But at the same time, it will reset when Panel loses power. So why would you use something like that? Well, besides our use as a placeholder for a formula, it's mainly used as an intermediate storage for values that need to be processed elsewhere in the UI. Now that I've created the internal tags for our clamp function, let's put them to use. Go back to where we left off, modify the formula by replacing PLC tag and constant values with our new internal tags. Once you validate the expression, you can save it as a user-defined function. Give it a name and a clear description, as well as descriptions of parameters. Save it, and voila! You have your own function within predefined list. Let's test it out. I'll add 3 numeric fields and link them to our internal tags: input, clamp max, and clamp min. Make sure to set the address type to right so we can modify them during the simulation. I'll also add 1 more numeric field with read access and link it to the clamp formula itself. Pay close attention to the arguments order. The software says them in the order they appear in the original expression. First the input value, then the maximum, and finally the minimum. Now let's run the simulation. If the input is 5, it is clamped to our minimum of 30. If we move the input within the range, no clamping occurs. But if we go above the limit, the value is clamped again, this time to the maximum of 80. Next step, we create a scaling function that maps our input values from the input range to the output range. Create more internal tags, add a couple of input fields, and then build the formula. Save this as a map function, and again, pay close attention to the order of arguments. Let's verify this in the simulation. We'll set our input and output ranges first. If we set the input to 30, it maps to 372. And input of 80 maps to 123. Any value within the input range is now correctly scaled to the corresponding value in the output range. We can take this one step forward by nesting the clamping function within our mapping logic. To keep the implementation clean, we can save this entire expression as a new function called scale_lim and use it to replace our existing code. Check it in simulation with input value 85. Yep, it is limited to 80. And then mapped to the output range. If we try 20, it works exactly as intended. Everything is in place, so let's get that needle moving properly. Navigate to the Y coordinate property and replace the existing formula with our scale limit function. Pass the temperature value as an input and use constant values as the limits. Let's see how it behaves in the simulation. Set temperature to 50, cool, 70, yep, the needle moves up to the corresponding tick. Try the value out of the range. Yes, it stops at the top of the scale. The other direction? Sure, it clamps. One of the best features of the text simulation is the built-in signal generator. If you double-click in the simulation column, you can set the signal type, which defaults to a sine wave, along with parameters like amplitude, vertical offset, and the repetition period. Once you tick the Enable checkbox and hit OK, the value will begin cycling automatically, and you'll see the needle moves in the real time. This makes the debugging process much more efficient as you don't have to manually change every value. To provide better context for the operator, we'll add a vertical light blue stripe to the scale to clearly mark normal operating window. That is T1 range defined in the temperature graph, from 42 to 80 degrees. Speaking of T1, I'll add a diamond shape next to the temperature needle and link its y-coordinate property to the T1 tag with scale lim function. It will act as a set point needle. In the next step, we'll need to set up the graph. Navigate to the Trends Charts folder and look for the real-time trend widget. You'll also see the history trend there, which is used for long-term data logging in non-volatile memory. But we'll save that for another day. For now, simply drag the real-time trend onto your screen. The Properties panel might look overwhelming at first, but we'll break it down step by step. The first parameter to check is page duration. By default, this is set to 5 minutes, which simply defines the span of your horizontal time axis. Next is the starting position. This determines where the current time point sits on the graph. Usually this is pinned to the right. In the behavior group, you'll find min y and max y, which defines the vertical span. We'll set it from 30 to 80 degrees. Finally, we have the most critical settings, the curve. This is where you assign the specific tag to be plotted and define exactly what the curve will look like on the display. Now I want to fit the graph to the left of the scale. By default, the widget includes several unnecessary elements like titles and scales that we don't need for this use. How do we get rid of them? Well, something could be disabled in widget properties, but we can also take advantage of ability to edit the complex widget. Double-click the widget to get into edit mode, and then just delete the title, labels, and scales. You can also modify the internal layout of the widget itself. Right-click on a column or row indicator and select Remove. This leaves us with only the core graph area. From there, we can jump into the widget properties to hide the grid and the outer frame. This results in a much cleaner look that is far easier to align with our bar graph. With the graph now properly formatted, we can extend our normal range indicator to the left as well. Finally, we'll place a numeric display beneath the graph to show the exact temperature value. And now the last component of the supply temperature control loop, valve status indicator. I'll start by duplicating our existing scale and adjusting its range to cover -100 to 100. From the widget gallery, I'll put in a standard vertical bar graph and set the maximum to 100 and the initial value to 50. The type is set to vertical and the color matches the blue from our established palette. Then link the value property to the opening tag from the valve control section of the PLC application. Adjust height, width, and position it over the top part of the scale. For the bottom half of the scale, we simply repeat the same steps. The only difference here is that we'll enable the reverse property and of course attach the closing tag. To enhance the visibility, especially when the opening-closing ratio is near 0, I'm going to layer a square needle indicator on top of the bar graph. To drive its movement, navigate to the Y property and enter the following logic. We'll use 250 as our base coordinate. Then add a 124 pixel offset for a close signal and subtract the same offset for the open signal. With that in place, run the simulation to verify that it works as intended. Return water temperature indicator is almost identical to the supply side. The main difference here, aside from mapping to the different tags, are that the normal operating range is both narrower and lower. The output for the return water temp control loop is linked directly to the pump speed. To reflect this, we'll add the actual drive speed to the right of the main bar graph. Since the underlying mechanic for this indicator are very similar to the valve indicator we just built, I won't dwell on the repetitive steps. Moving on to the pressure values, we'll start by adding a scale and a rectangular anchor as our base. Then the normal range for the discharge pressure. Just as we did before, we'll add a trend graph, a needle indicator, and a numeric display, making sure, of course, to map these to the correct pressure tags. Since we are monitoring a pump, the discharge pressure is only half the story. We also need to keep a close eye on the suction pressure. To reflect this on the interface, I'll add a second needle to the graph and link it to the suction pressure tag, along with its own numeric display. Unlike our temperature indicators, pressure monitoring involves critical fault thresholds. For example, suction pressure falling below 2 bars can lead to a dry run condition. To ensure the operator's attention is drawn to this kind of abnormal situation, let's add a visual clue for these alarm states. Add a rectangle with a solid fill that spans the entire fault range for these pressure values. For the fill color property, we'll define a color palette, a muted gray for a state of 0 and a bright red for a state of 1. We'll then link this to an internal tag that monitors whether either pressure value or both has dropped below the dry run threshold. We can apply the same logic to high pressure scenarios as well. This ensures that whenever a value drifts beyond the safe limits, the respective zone on the interface immediately shifts to red, alerting the operator to the issue. Now, you might be wondering how the internal tag actually receives its value. I'm getting a bit ahead of myself here, and I promise we'll dedicate an entire chapter to this later, but the logic is handled by a script, which is triggered every time any pressure value changes. To visualize the pump head, or the pressure differential, I'll add a bar graph and increase its width to make it stand out. In its default configuration, the bar graph displays the difference but remains anchored to the bottom of the scale. To make it more intuitive, I want the base of this bar to slide together with the suction pressure needle. As you've probably guessed, we achieve this by linking the suction pressure tag to the Y-coordinate property. We also need an indication of critically low pressure head. To handle this, I'll link the bar's color property to a low pressure difference tag and apply alarm palette. Let's do a quick validation. As expected, the bar turns to red the moment the differential drops below 1 bar. Ambient temperature indicator doesn't introduce any new techniques. We can simply duplicate one from our existing indicators, strip away the unnecessary elements as we did before, and remap the tags. Of course, you aren't limited to a standalone dashboard. You can easily integrate these high-performance elements directly into your process flow diagrams to get the best of both worlds: situational awareness and functional context. Stay safe, and I'll see you in the next one.